Hello everybody, welcome back to Physics 425. What we've been talking about in the last video was transfer of heat between surfaces at two different temperatures via radiation. And so in that process we didn't require anything between these two surfaces. It could be a perfect vacuum and there's still going to be some radiative heat transfer. What I want to talk about today is heat transfer between two surfaces at different temperatures, but when there's a residual gas between those two surfaces. So how does gas conduct heat from the hot surface to the cold surface? And so we'll have to establish a couple of things before we can get the result that we want. And the first thing we're going to think about is the mean free path of a gas particle. And so we're going to imagine some kind of container that contains gas at a certain pressure. And the mean free path tells us how far does a particular gas particle move on average before it scatters off of another of the gas particles. And we're going to be working with what's called a quasi-ideal model of gases. So to understand thermal conduction in a real gas, we need to consider collisions between gas particles. All right, so a gas for which the thermodynamic properties are determined by the ideal gas approximation, in which PV is nKT, but in which the molecules undergo collisions is called quasi-ideal. So the ideal part of it is that we're assuming that the ideal gas law holds, but usually the ideal gas law considers a very low density of gas so that the interaction between gas particles is very rare and can be neglected. And so we're going to relax that a little bit and we're going to allow for some collisions. And so what we're going to do is we will consider elastic collision. So an elastic collision is one in which the kinetic energy is conserved. So kinetic energy is conserved. And these elastic collisions will result in scattering of the particles. So if we consider any pair of particles, they will collide if their centers come within 2r of each other, where r is the radius of one of the particles. And so if we think of a pair of particles, maybe here's one that is moving in this direction, and we'll say that this particle has some radius r, And so let's extend this line. I'm going to draw a parallel line that just meets it, the outer circumference. And then there's another particle over here. Here's its center, and here's R. And so the distance from here to here is 2R. We define a scattering cross-section, which is an area that is going to be given the symbol sigma c, and it's a disk of radius 2r. And so if you have one particle sitting there and any other particle comes within this disk of area pi times 2r squared, then there's going to be an interaction, a collision between these particles. Okay, so let's suppose that we have a system where there are little n particles per unit volume. So it's a number density, little n particles per unit volume. Okay, so I'm going to try to draw a certain volume here, and we'll make this look something like that. Okay, can maybe improve this slightly. Okay, and so I'm going to also say that there's an x-axis that is going to pass through this volume of space, and x. And so I'm going to say that this position here is position x, and this position over here is x plus dx. So that this slab of space is a width of dx. Okay, and so in here are particles, and these particles have radius r, and they occupy some of this volume. And then over here we have another particle, and it's sitting at the position x equals 0. So it's starting here at x equals 0, but it's moving along the x direction towards this slab of other particles. Okay, so that's the scenario. So in a layer of thickness dx and area A, so the side of this box has area A. So this area A is perpendicular to the direction of motion of a particle, and so we're assuming that we have a particle moving in the x direction. So this this area A is in a plane that's perpendicular to the x-axis. Particle moving in the x direction, there are, so how many particles are there? If we have n particles per unit volume, and the volume of our slab is the area times the thickness, then there are this many particles, NaDx particles, each with scattering cross-section sigma c, which was this pi times 2r squared. Okay, so the total scattering cross-section inside this volume of space is the scattering cross-section per particle times the number of particles. And so what we could do is we could say that the probability that an incoming particle moving in the x direction the probability that it is scattered in x to x plus dx is the scattering cross-section, which is an area, divided by the total area that's available for it to pass through. And so what happens is these factors of A cancel, and it's the scattering cross-section times the number density of particles times the thickness of our slab. Alternatively, we could say that the probability that the particle gets through a region of thickness dx is 1 minus the probability that it's scattered. Okay, so let's define some quantities then. So what we'll do is we'll assume that our particle originates from the position x equals 0. Okay, and so that's what we drew up here. So it starts at x equals 0. The first thing the particle has to do is it has to make it to position x. And I've drawn particles as if they're only in the slab, but there are also particles out here in space, right? There's a uniform density of particles. And so if our particle's even going to make it to x, it would have to not scatter from any of the particles that are in the region of space between x equals 0 and the position that we're calling x. So the probability that our particle makes it to x without scattering is, we're going to define that to be p of x. Okay, so right now we don't know what that is, but we're going to try to find out. The probability that the particle goes from x to x plus dx without scattering is, so if we had a particle starting at x, the probability that it makes it to x plus dx without scattering is what we just calculated above. It's 1 minus the scattering cross-section, the number density of particles, times the thickness of the slab. Okay, so that means what we're going to be interested in is I have a particle that starts at x equals 0. I want to know what is the probability that it makes it to x without scattering, and then also makes it to x plus dx without scattering. Well, if you have that kind of condition that something has to happen, and then something else also has to happen, then the probability of that occurring is the product of the two individual probabilities. So the probability that particle initially at x equals 0 goes first to x unscattered, and then to x plus dx without scattering, is the product of the two. And so it's px times 1 minus sigma c n dx. And we're going to call that p of x plus dx. And so just to try to be clear, this is the probability that we go from x equals 0 to x plus dx without scattering. P of x is the probability that we go from x equals 0 to x without scattering. And this factor here is the probability of going from x to x plus dx without scattering. Okay, so that's quite nice because we can do something with this. We could distribute the p of x, and then we could have p of x plus dx is equal to p of x minus p of x sigma c n dx. And then we could subtract off the isolated p of x and divide by dx. And that would lead to p of x plus dx minus p of x. And then we divide by dx. And what would be left over on the right-hand side is minus p of x, scattering cross-section, and the particle number density. But of course, if we take the limit that dx goes to 0, this is just the definition of the derivative of p of x with respect to x. And so that means we could write p of x dx is equal to minus p of x sigma cn, or dpx over p of x is equal to minus sigma c n dx. Okay, so let's integrate. So when we integrate, we'll go from, we start from a position of x equals 0 and we end up at some other position x. This integral that we're going to do is just going to lead to a natural log. And so on the other side, we integrate from a position x equals 0 to some other position x. And then we have a bunch of constants, the scattering cross-section and the number density dx. Okay, so this is going to be the ln of p of x over p0 is equal to minus sigma c n times x, or solving for p of x. P of x is equal to p of 0 e to the minus sigma c n times x. So if you think about a little bit how we've defined what we mean by p of x, let's go back up here. P of x is the probability of going from x equals 0 to x without scattering. So if we stay consistent with that, then p of 0 is the probability of going from x equals 0 to x equals 0 without scattering. But of course, if I'm already at x equals 0, then I don't have to move anywhere to get to x equals 0, and so there's no chance that I'm going to scatter, and so that means the probability that I get to my starting point without scattering must be 1. And so that's our integration constant, and that means that if p of 0 is 1, then we can write p of x, the probability of making it to some position x without scattering is going to be minus sigma c n x, and that's usually written as e to the minus x over L, where L is defined to be 1 over sigma c n, and L is called the mean free path. Of the particle. We can check that the units make sense because n is a particle density, so it has units of 1 over meters cubed. Sigma c is a scattering cross-section, a cross-sectional area, so it has units of meters squared. So the product is units of 1 over meters, but that's in the denominator, so L, the mean free path, has units of meters as expected. What it represents physically is the mean free path is the distance, let's say it's the average distance that a gas particle travels between scattering events. So the mean free path goes down as the number density goes up, and that makes sense because as you increase n, there's just more particles to scatter off of. They occupy more of the available volume. And also as the scattering cross-section goes up, the size of the particles goes up, then the mean free path goes down. So as expected, the mean free path is inversely proportional to the number density. And so that means higher density results in a higher collision rate between particles, and therefore a lower mean free path L. So for these microscopic particles, the radius of the molecules is not a well-defined thing, but you can work out, say, an effective size of the particles. So the radius R of gas molecules is not well defined, but we can work out an effective radius of, say, nitrogen or oxygen molecules. And it's on the order of 1.5 angstroms. An angstrom is times 10 to the minus 10 meters, which is equivalent to, let's see, I guess it's 0.15 times 10 to the minus 9 meters, or 0.15 nanometers. Okay, so for an ideal gas at room temperature, the number density is N over V, but from the ideal gas law, that's P over kBT. And so if you put in an atmosphere pressure, it's about 100 kilopascals, and divide by kb and 300 Kelvin, this comes out to be around 2.4 times 10 to the 25 particles per cubic meter. And so then the mean free path is the scattering cross-section, which we can write as pi times 2r squared, where r is this effective radius. And then we have the number density. And if you put in the numbers, this is about 140 nanometers. And so this is a typical mean free path for an air particle at standard temperature and pressure. Okay, this mean free path is going to be a useful quantity for us when we start to think about the conduction of heat by gases. And so we're going to try to calculate the thermal conductivity of a gas. And so the way we're going to do this is we're going to think of two boxes. I'm going to make the box have a width that's equal to the mean free path of the gas particles. And then I'm right beside it, I'm going to put another box which is the same. Maybe I'll make it a little bit bigger so that it looks about the same. Okay, so this second box is also a mean free path wide. And so this is box 1, and this is box 2. These aren't closed containers, they're open containers, and so that's why I've drawn them as dashed lines. And so gas particles can move around and pass through the boundaries. And so there's some gas particles initially in box 1, and some gas particles initially in box 2, and they can pass through the boundary that separates the two boxes. And I want to imagine the center of this first box. So here's some position in the center, and if we were to measure the temperature of the gas, we would get T1, and then over here at the center of the second box, we measure the temperature of the gas, and that's T2, and the distance between these two centers, the way we've constructed our geometry, is L1 mean free path. And so the goal is to attempt to calculate the heat flow that crosses the boundary between box 1 and box 2. So if T1 is hotter than T2, we'd expect a net heat flow from box 1 into box 2. Okay, so we know a gas particle can move on average a distance L without scattering, and so we could calculate the time between scattering events as the mean free path divided by the average speed of the particle. So this delta t is the average time between collisions, and v bar is the average speed of gas molecules. So hotter gas molecules would have a higher average speed. So let's consider a gas molecule that crosses the plane from left to right. So from box 1 and into box 2. So this particle will obviously will have started somewhere within box 1. Okay, if we think about this, all of these particles, if let's say this particle was moving to the right, if it was moving to the right, it would move a mean free path L before scattering, and if it did that, it would end up in box 2. And so all of the particles in box 1, all of those particles that are moving to the right will end up in box 2 in a time delta t. Likewise, all the particles in box 2 that happen to be moving to the left after a time delta t will end up in box 1. Okay, so if the total energy in box 1 is U1, then the energy crossing the plane from left to right is approximately U1 over 2. And so this is definitely approximation. We're assuming that half the molecules moving to the right, and so they enter box 2, and half are moving to the left, and so they do not enter box 2. It's an approximation because, of course, particles might be moving up or down or have components of velocity into the page or out of the page. And so what we would think then is we're probably overestimating how much energy transfers from box 1 into box 2. But let's go with this. If half the particles from box 1 end up in 2 because they're moving to the right, then the amount of energy that's moved into box 2 is U1 over 2. Of course, we could make the same argument for box 2 particles moving into box 1. So we have U2 over 2, amount of energy moving from right to left across our boundary. Okay, so then we could calculate the change in energy of box 2. So let's call that change in energy Q. And so it's going to gain an energy 1/2 of U1, and it's going to lose an energy of 1/2 of U2. So it's accepted particles from box 1, and it's lost some of its original particles. And so we could write this as minus 1/2, and this would be U2 minus U1. Okay. So we could express this internal energy change as a heat capacity. So remember, heat capacity is a relationship between how much energy you add to a system and what the resulting temperature change is. And so this delta U we could write as the heat capacity times delta T. And so this is going to be the CV will be the heat capacity of particles in one box, right? Because we're talking about the heat that was added to box 2, and that's dependent on the particles that are in box 2. Okay, so this Q is then going to be equal to minus 1/2 times the heat capacity times the temperature difference. And so T2, as we've already indicated, is the average temperature in box 2, which we obtain by, say, measuring the temperature in the center of the box. And T1 is likewise the average temperature in box 1. Okay, the temperature gradient temperature gradient is dt dx. So how does the temperature change with position? But if we go back and look at our original picture, our change in position between T1 and T2, our dx, is just L, a mean free path, and the change in temperature, dt, is T2 minus T1. And so delta T is the temperature gradient times the change in position, which was our mean free path. And so this is equivalent to T2 minus T1, and what we'll do is we'll substitute this expression for the temperature difference into our heat expression. And so what we're left with then is Q is equal to minus 1/2 times the heat capacity, and this delta T becomes the mean free path times the temperature gradient. And so we're close then to being able to write down an expression for the thermal conductivity of our gas, because by definition, the heat flux is the energy change per unit time per unit area is going to be minus kappa, the thermal conductivity, times the temperature gradient. And so this is kappa, and it's the, kappa, and it's the thermal conductivity of our gas. And so if we take our Q and divide by delta T and divide by an area, we get minus 1/2 CVL over A delta T times the temperature gradient. And that means that everything here is the thermal conductivity. And so the thermal conductivity of our quasi-ideal gas is kappa is about equal to the heat capacity times the mean free path divided by 2 times area times delta T. Now, that's not great because we don't want our thermal conductivity to be dependent on some kind of geometrical factor. So let's try to re-express this. A geometrical factor like the cross-sectional area, like what area are we talking about? So for our scenario, we know some of these things. Delta T is the time between average collisions, and that was the mean free path divided by the average speed of the particles. The volume of our boxes is whatever the area is times the mean free path. And so the area is the area of the box that's perpendicular to the screen, and so it's not in our picture. But if we had our boxes, it might look something like this. So here's one of the boxes, and then right beside it is the other box. And so we said the width of the boxes was the mean free path, and this is going to be the area. And so A times L is the volume of the box. And so that means, let's see, if we substitute these things in, kappa is going to be the heat capacity times the mean free path divided by 2. And so for the area, we'll put in volume divided by mean free path. And for delta T, we'll put in the mean free path times the average speed. And so we can do some cancellations here. And we get 1/2 the heat capacity divided by volume times the average speed times the mean free path. So let's write the heat capacity CV as the number of particles times the mass of each particle times the specific heat. And so this is the number of particles. This is the mass of each particle. So if it's nitrogen or whatever, it's the mass of a nitrogen molecule. And this is the specific heat, or the heat capacity per unit mass, right? The heat capacity of the gas, the total heat capacity determines on how much gas there is, right? If you double the amount of gas, then you have to double the amount of heat you put in to change the temperature by the same amount. So what the specific heat does is it divides out by the amount of stuff you have. And so we're going to write that as the specific heat per unit mass. And so I'm trying to use capital C for a heat capacity and little c for a specific heat. Anyways, if we make those changes, then we get kappa is about equal to 1/2. And so for the heat capacity, we'll write N m times the specific heat, then divide by volume, then the average speed, and then the mean free path. But N divided by V is the number density, then the mass of the particles, the specific heat, the average speed, and the mean free path. And there we have the thermal conductivity of our quasi-ideal gas. So if you did a unit analysis, the units of thermal conductivity turn out to be watts per Kelvin per meter. And so finally, the last thing I'll say, I think, in this video is the following. We did an approximate calculation because we assumed that all of the particles in box 1 were either moving left or right, and the same thing for box 2. We didn't allow for the fact that, you know, the velocity of each individual particle, which is going to have 3 different components, and so we neglected all of that. So a full but difficult calculation or treatment is going to give that kappa is going to be, like we calculated, the number density times the mass of the particle times the specific heat times the average volume times L. That's all the same. What's different is the prefactor. So instead of 1/2, you get a 1/3. Okay, so the correction is changing the 1/2 to a 1/3. Okay, good. So that's where I'm going to stop for right now. We'll have, I think, a little more to say about the heat transfer by a gas between surfaces at different temperature, but we'll take that up in the next video. All right, thank you very much.